Hello and welcome to this video on single replacement reactions. We're going to take a look at what happens in a single replacement reaction, and then we're also going to be able to use some tools to determine if a single replacement reaction will occur or if it will not occur. And so grab your notebooks and something to write with, and let's get started. I have a couple pictures here, and if you take a look at these pictures, we'll find out that this is actually just a blown up version. So this is a piece of copper wire that's coiled up, and it was placed into silver nitrate solution. And the silver nitrate solution originally is a clear color when it's made. And what we see is that there's a single replacement reaction occurring. So what happens is this copper in the wire is actually replacing the copper that's in solution. So this aqua color you see is actually copper nitrate solution, and then all of this is silver being deposited on the outside of that copper wire. And so it's a pretty interesting thing to see. We'll do a demonstration of that in class so that you guys get to see it. And so this is an example of a single replacement reaction occurring. So we took a look in the previous video on single replacement reactions, and we had this generic kind of equation for this. And so what we see here is that we start off with a substance that's by itself, okay? And that substance that's by itself will replace the other thing. And so this one actually ends up replacing B. So A replaces B here. And so over here we see that A is now with X and B is by itself, okay? And that is the general process that we see. Now, it's possible, and one thing that you're going to see today is that we could have A plus BX, okay, end up forming X plus BA, depending upon whether this here is actually going to be a cation or an anion. So when we get to the end of this video, I'll come back to that concept and we'll take a look at that again. But the idea is, no matter what, that one thing is going to replace the other thing that's going to be equivalent to it. So let's take a look at when this happens with metals. Okay? So metals are an example of when this will happen. Move me up over here. And so you're going to want to definitely write this down. This is a really important part. And it says that we have this thing called an activity series of metals. And so in a single replacement reaction, if the solid metal is more reactive than the metal in the aqueous ionic compound, then we will see that the reaction will occur. And so we have an activity series that helps us to do this. And so let's take a look at that activity series. It's right here. And so we see that at the top of this are the most reactive. Okay, so these up here are going to be the most reactive, and at the bottom they're going to be the least reactive. Okay, and so it goes from greatest in reactivity down to the least in reactivity down at the bottom. And so you'll see down at the bottom our jewelry metals tend to be not very reactive, and that's actually a good thing. You don't want to be wearing a necklace and have it start reacting with you. And that's one of the reasons why when people wear jewelry that say has zinc or nickel in it, a lot of times they'll have allergic reactions to them, because those metals actually tend to be a little more reactive than silver or gold or platinum are. So when we take a look at this, we can actually see an example of that, and I'm going to do an example. So that picture that we saw at the very beginning started off with copper that was the solid, so we do need to use those states of matter when we do these. And then we added to that some silver nitrate, AgNO3, okay, and that was aqueous. And we ended up producing silver, so Ag. The silver didn't come from nowhere. It actually already occurred in the solution itself, and that'll be a solid that was deposited on the outside. And then we produced copper 2 nitrate, was actually what the solution was. So CuNO3 2, put the 2 here, can't really quite see that. And then that is actually also aqueous. So we'll balance our equation. So we have 2 of those, so we need 2 here and a 2 here. So this reaction occurs, and this is a single replacement reaction. And so we see that this solid copper is more reactive. And so if you look over on this chart here, we see that copper is more reactive than silver. So if we're moving this way, copper is going to be more reactive. And that means that this will occur. So this reaction will occur. Now, we could see the opposite of that. So we could start off with silver, and I will hopefully be able to do an example of this if I remember a piece of silver jewelry. So we can start off with silver. So if we start off with silver metal, Ag solid, and we put that into copper Cu nitrate, NO3 2, so copper 2 nitrate, and that'll be aqueous. We end up producing nothing because there's no reaction that will occur. So we say no reaction. And the reason why is if we take a look back over at that chart, we see that silver is actually below copper. And so silver is the solid metal. And if it is less reactive than the thing that's in the ionic compound, there will be no reaction. So we can write NR or no reaction there. And so that will not occur. And that's always the case. So if it's the solid metal, it will replace anything that's below it, but it will not replace anything that's above it. And so that is a very important concept, and you will be working with that in class. All right. Let's take a look now at what happens with nonmetals, okay? So with nonmetals, you see that there's an activity series for halogens, and the single replacement reaction occurs only when the single halogen, the halogen that's by itself, actually is more reactive than the halogen in the ionic compound. And so this works very similar, but we're going to have a different reactivity series for this. So we see that fluorine is the most reactive, and that as we move down, these are going to become less reactive. Oops. Let's go back there. So here's an example for us. We could have F2, which is a gas. Remember, that's one of our diatomic molecules, and those are gases in nature. And we could actually run this gas into a solution that is made of sodium chloride. So we could put it just in a salt solution. So NaCl, and we'll make that aqueous because it's in solution. Okay. And actually what happens is because fluorine is more reactive, okay, so it's higher on this list, it's more reactive, this reaction will occur. And so we end up forming chlorine gas, which is Cl2, remember that's another diatomic gas, plus sodium chloride, or excuse me, sodium fluoride, NaF2, or NaF. So to balance this, we need to put a 2 here and a 2 here, okay? And this was aqueous. And so this one will occur. Now the opposite of that, if we started with chlorine gas and we added to that to sodium fluoride, okay, no reaction would occur. So if we move the other direction, say we move up here, get some turquoise, and we move from chlorine being the single thing and trying to replace fluorine in the compound itself, we know that this will not happen, okay? There is no reaction here, and so that means there's no reaction. And we don't need to balance anything or do anything else. So whenever we see something that's more reactive as the individual thing, it can replace the thing that's in the compound. And that's what we're really looking at. So let's kind of do a little recap here and see another example of each. So here are the metals. Hydrogen, when it acts as an ion, it will be on that list as well. And you guys will get a copy of that in class so that you can take a look at those. So metals or hydrogen ion, which will replace a metal as well. Here's an example. So if we see that magnesium, so magnesium is going to be our single metal, and magnesium happens to be more reactive than zinc, so magnesium ends up replacing zinc in this, and we end up with zinc being by itself and magnesium going into the compound, okay? And so we'll end up with zinc being deposited. And we can also see the same thing, and here's another example. So the halogen is an anion, and it will replace the anion that's in the compound. And so we see here chlorine, it cannot replace nickel. It has to replace bromine because those are the two things that are equivalent. So here's where the anion replaces the anion and the cation replaces a cation. And that's a pretty important concept. People sometimes will get those mixed around, and you want to be sure that you are replacing equal things. And so if it would form an anion, it has to replace the anion. If it would form a cation, it has to replace the cation. And that's the way that single replacement reactions occur. And remember, they only will happen if the thing that's by themselves is more reactive than the thing that's in the compound. I hope that was helpful.